Okay, so we did turn on recording, and we are going to now look at applying SPM to fMRI data in Matlab. And as I mentioned earlier, the advantage is that in that case we can use the package, but we can also use our own homemade scripts and different Matlab commands to interact with the data and do our own data analysis. So for instance, in Matlab, you have the commands nifty read and nifty write to read and write the volume data that is being recorded in the functional MRI. And you can also use all kind of display functionality that is available to look at the slices or at the volume. So that's kind of really neat. So I'm now going to change my my share to the Matlab share, and if you ever want to do this, this gives you all the information that you need to download SPM version 12 in this case, and also the data that we are going to use from a flanker test. There is a nice website that explains how that test is being done, and that you can download multiple data sets from different patients. We are just doing this as an example, so we are not going to look at different patients and compare statistics and what have you. We're just going to do the basics from the SPM12 with a demonstration how you can interact with that package. So let me stop share and share my Matlab screen now. So here you can see my Matlab screen. And if I start my fMRI version, I typically type SPM fMRI because SPM can do also different modalities. So you have to say I want to run SPM, but I want to run the fMRI partition. And then you will see that this will take a little bit of time. You will get an initialization. And then after a while you will get this double arrow to indicate that things are ready. Now it has opened, and you haven't seen that because I only shared this one. It has opened a number of windows, and I'm going to again share these windows by sharing my whole screen now. And now you can see my my whole screen. And one of the windows is the let me kind of get rid of this. Is this dialogue that allows you to interact with the data. So here you see, by the way, all the pre-processing that we just discussed in the handout. So how you can co-register, how you can realign, how you can correct for the slice timing. So all the pre-processing can be done in SPM12, and you don't need to kind of make your own algorithm to do that. There is another one that if your data that you get from the scanner is in DICOM format rather than in Nifty format, you can use the DICOM import to kind of convert it to a Nifty file. So that's kind of really neat, isn't it? If you then have Nifty files, you can use this to display the data. And I already have this in the typical format where you have the anatomy and the function. And you can see that in this bits format here, I have a subdirectory function. And in the subdirectory function, I have two tests, flanker run 1 and flanker run 2 for this particular patient. So if I click on this one, I select it. You can see it, it kind of happens here. And you click done, and now it will show you the data as it has been recorded. So this is the raw nifty data without any pre-processing and without any realignment and stuff like that. You can play with it. You have a cursor here. And while you play with it, you get an adjustment here, what your hair position is. So you have a nice way of dealing with the data, looking at the data, and do whatever you think is kind of useful. So that's the part that allows you to kind of look at data and pre-process it and analyze it. I kind of recommend there are a number of YouTube videos that are very good in giving you the different steps that you follow to do all this. And for the nerds amongst you, I kind of pre-warn you, it's kind of addictive once you get to play with it, because it's a lot of fun. And I don't want to do that now at this point, because that would be, A, it takes a lot of time, and B, it would just be duplicating stuff that's already available on YouTube. What I want to do is kind of show you what kind of stuff you can do if you wanted to do your own homemade algorithms. And this is an Matlab script reading one of these data files that we are just looking at in the other window here, in this one. The script actually is also part of the handout. So if you look at the appendices of the handout, you can find that script as well. I have it here in my Matlab routine. So it's called fMRI ANL.m, and it's just for kind of demonstration purposes. So first of all, we read the data and the header information. So you need the volume, and you use Matlab. Matlab actually has done this very nicely. There is already a command nifty read, so you don't have to hack the data. You can directly read it. You can also read the header information. That's basically the information that tells you a lot about what's going on here in these windows. And then you can start doing stuff. In this case, you know what the relaxation time is. You can find it on the website. Your relaxation time is also your sample rate, because that's the time at which the images are being taken. And in this case, what we are going to do is we are going to filter this with an FIR filter. And we're going to do an analysis of the frequency that is taking place. So we are having a matrix for the filter, and we have a matrix for the power. And then here is a loop that you can see. I just determined the size of this image. You can always find that here if you don't know it, but you can also find it in your header information. So you have a size from 64 by 64 by 40. So 40 is the time, and 64 is the Z domain, and 64 and 64 are the X and Y pieces. And here you can see that I didn't want to do that. So here you can see that we are going through a number of things. We demean the data. One of the things you have to do is that once you are in Matlab, Matlab wants to compute with float numbers, with reals, whereas most of the data from the scanner that come directly are kind of unsigned or signed integer. You can kind of figure out what it is by looking at it. But in this case, what I do is I take the signal, and then I kind of turn the signal into a double. So it's a float. So now I can do the computation. So that's the reason that this command is here. If you omit that command, filt, or the filters will start to complain about that. And also the FFT will start to complain about it. That's because Matlab really wants to deal and compute with floats, and preferably doubles. So here you see that I now do an average. I do an average for the power spectrum. I do an average for the filter. and then I plot the data. And what's kind of nice is I also show a section in the XY plane, so I can use my own command to look at the section of what I have been doing, and I can show that. And then, which is really powerful, I think, because now you can really interact with your SPM package, is now you can take your process data and save that as a Nifty file. And that Nifty file can then be read again by the SPM package. So that's kind of what I see as a huge advantage for people that are already kind of used to Matlab, have Matlab available, and want to do their proprietary stuff with it. So now let's run this program and see what it is doing. And it takes a little bit before it kind of shows you what's going on. Now, while we speak, it is computing the power spectrum, and it is computing the filtered data and the display of the slice. So here is the slice. Sorry, it's a bit small, but I could have blown it up a little bit further. This is the filter result, and this is the power result. So here you see the power spectrum, and of course the frequencies are really low because the sample rate is really low, and here is the amplitude. I actually show it in a log-log scale. In the handout I show it on a linear scale, so that's it's the same spectrum, but I sometimes like to look at the log-log scale to see to what extent we are dealing with a 1/f spectrum. And here you see what we did with the average filter response. You see here the raw data. This is the average bolt that we have been recording. That's the red signal. And in blue, you can see that what it is if we look at the filtered result. And in the meantime, it has now also looked or stored the data that we produced, because now you can see that in addition to the raw flanker tests here, run 1 and run 2, we have now also a Nifty file that says the filter data, and we have a Nifty file that says the amplitude spectrum data. So we can now use all these files to kind of look at the data. And of course, you can play with this. You can kind of filter with different areas. You can do stuff that Dr. Benayoun was also kind of talking about. You could look at correlations between voxels and other voxels. You can do an independent component analysis or a principal component analysis to see where different components are in your volume. And you can then do all these things. You can do that in Matlab, and you can then display it. I think that's kind of the part that I wanted to show you from the proprietary data set. Now I also want to show you one thing that you then can use if you display stuff in the unit, which is that if you are looking into this Nifty file, and you wanted to kind of look at what the data looks like, more like we are used to looking at it, then you can basically do a right click, and then you can hit browse, and then you get basically your own thing, your dialogue again. And by the way, notice that you now have the amplitude spectrum and the filtered data. We can now say, well, let's kind of look at this data that we now have in the display. And I'm kind of going to pick out the run 1 data. So I say, well, anything that has run 1 in it. Sorry, I have to do that here. Everything that has run 1 in it here. And the rest is dot star. so that doesn't matter. And I'm now typing it in like it's in the handout. So I'm going to look at images from time steps 1 to 250. And now I'm going to say hit enter. And now you can see that it kind of shows you in the dialog where all these different steps are, time steps are. And now you right click and you say select all. And then basically you hit done. And now the nice thing is you can, in this window, you can now kind of go through the data, and it will now show you in the spatial domain here how the different time steps work. So that's kind of this dialog here. And you now see that the cursor is moving here, and while the cursor is moving, you can see that the images are being adjusted. So you can look at a movie of your data. So you can of course say, well, that's all nice, etc. But I also would like to see, for instance, what my signal is looking at this point. And then you right click again, you say browse again, and then you say display profile. And now you can see what the signal is at this voxel. So this is the voxel that you are looking at, voxel at 43.2, 32.5, and 32.7. So of course you should round this to get real voxels, because voxels are integers, but apparently this is not exactly the position here. You can also kind of type in a number here if you want, or you can just move your cursor to a different voxel. And if you do that, you can see that while you're going to a different voxel, this area that shows the data is also going to kind of show you different data. And so you can basically do a lot of stuff. And if you were interested, hey, what's going on here, you could kind of put your cursor there, and you get your data, which is really nice, of course. If you wanted to check in Matlab again, so well, I have this, and I think that's another one that I will use the same values here. I will kind of take voxel 43, 32, 32. No, sorry, I shouldn't have put commas there. Sorry. 43, 30, 32, 32. Now it's mad at me. 43, 32, 32. So now you see that this voxel is basically jumping. The curve is making sure that the crosshair is jumping to that voxel, and also the data that is associated with this voxel is also kind of displayed now in this Matlab routine. So now if you kind of have read the data, and I think I still have that available here in V, let me check if that's the case. I still have my volume V, see, here it is. And now I can say, well, I want to kind of look at this voxel directly in Matlab. I can say, well, my voxel is going to be this time series, and that is going to be the V, which is my volume, and now I'm using the same values, 32, 32, and I'm going to take all the data here. And so now I'm just kind of using this command to make a section in my volume, and I'm putting it in a voxel, and this one should be here. So I think this should kind of do that. And so now I can make another figure here, and I can plot this voxel 1 And I'm going to kind of make sure I can distinguish it from the other one. I'm going to give it a different color. I'm going to plot it in black. Now, basically, you can see I just can compare what I just cut out of my volume that I read with the Nifty read, and I can kind of compare that what I kind of just read with this voxel with SPM, and you can see that they are nicely the same. And so this is how you can directly interact with your data set, which I think is quite useful and powerful. Okay, then I want to end before I stop the recording and before I hang on for questions. I want to end with showing you this screen, which is some online resources you have, which is kind of the stuff that we have discussed before. The lecture from Dr. Benayoun that you have seen, but this one is the lecture from last year, which is pretty much the same or similar. Then the SPM home link is here. One that's really good, you have Andy's Brain Book, and that's a YouTube, but you also have it in a text format, so that's really nice. The data that we have been using is available on this link, and then there is a really nice text on fMRI available online, and I actually have the book itself. I still like to read real books, so I have this book that you can probably get from the library as well, which is a really nice textbook for fMRI, and it's also combining this with EEG, which is one of the projects that my lab is going to look into, or our section is going to look into in the near future. So that's kind of where I want to stop the recording, and I'm going to hang on for some questions, comments, conversation.